Good morning, and thank you for joining us today for this Maya HTT NASA webinar detailing exciting functionality within Simcenter 3D Space Systems Thermal, targeted at streamlining the thermal simulation process. We plan to conduct these webinars for NASA bi-monthly with a continued focus on software tools that make you, the thermal analyst, more efficient and productive. My name is Carl Poplowski. I manage the Engineering Simulation Services Group at Maya HTT. And we have with us today Joel Rooks and Dave Zoisman from Siemens, Christian Semler, Simcenter 3D Thermal Flow Program Manager at Maya HTT, and John Frederick Ruel, Senior Applications Engineer at Maya HTT. Joel will be saying a few words, and then Christian will provide a brief introduction to Maya HTT, followed by an overview of the Simcenter 3D Thermal Flow software tools, including Space Systems Thermal. Then John Frederick will discuss and demonstrate user-friendly mapping of 3D boundary condition data in Simcenter 3D Space Systems Thermal with a focus on its many applications and the benefits of time and effort to the user. Audience microphones will be muted during the presentation. If you have questions, please use the question panel on your GoTo dashboard. All questions will be held and answered at the end of the presentation. We hope you enjoy the presentation today and find the information useful. And please note that this webinar is being recorded. I'll now turn the mic over to Joel. Thank you.
Thank you, Carl. Yeah, this is Joel Rooks with Siemens. I'm one of the account managers that works with Maya and manages our activities at NASA. The other one is Dave Zoisman, who's on the line. I'm introducing him just for the sake of time here. But appreciate everyone for attending, and I also thank Maya for putting this together. And we're looking forward to working with you on all your thermal analysis activities in the future. Thank you.
And Carl. Now Christian will take over.
Yeah, good morning, everybody. It is a great pleasure for me to launch this first webinar of what I hope will be a series of many webinars that we plan to develop for NASA. My name is Christian Semler, and I'm the Thermal Flow Simcenter Space System Thermal Product Manager here at Maya. Just as a quick background, I have been with Maya for 2 years now, and I'm responsible for the development of a global strategy for my products. I've been involved in simulation for over 25 years and held different positions, but in my role today, I feel privileged to have a direct impact on the product that customers like NASA use. Part of my role is to understand what the industry is looking for, and part is to spread the features that make our solution particularly useful. Some of you may be confused since most of the time you interact directly with Siemens while I introduce myself as an employee of Maya. So I thought I would just give a quick overview of Maya. GF, can you go to the next slide? So Maya provides software-driven engineering solutions. We are very proud to have been awarded this year the #1 worldwide partner for Siemens. We are passionate engineers. We have over 200 employees located in the US, in Canada, and in the UK. 75% of our staff are scientists and engineers, of which 1/3 are holding PhDs. Although we started in space and are recognized worldwide for our multi-physics simulation. Our engineers have sought after hands-on experience in almost every industry. It's not a joke, but from satellite to tomatoes, we do it all. We not only developed over 30 software modules for Siemens, but now have millions of users all over the world using our software. So we help our clients put satellites in space, reduce energy consumption of data centers, design zero-emission vehicles, deliver tomatoes to customers, and find better ways of doing engineering. Next slide. So since this is our first webinar, I thought you might be interested to learn about our history. As I said earlier, our DNA is intimately linked to the space industry, as our founder was a thermal engineer for a satellite company before founding Maya HTT. He studied the development of an element-based finite difference thermal solver that eventually became TMG, or thermal model generator, that was released 2 years later, and that is very often still referred to with this name in the thermal space community today. ID's TMG was first released in 1988, and it was, and actually still remains, with today under the Simcenter brain, the only spacecraft thermal analysis code that is fully embedded in a CAD CAE platform. To make a long story short, SDRC was bought by UG and now belongs to Siemens. And they introduced the NX software package as the successor to IDs and Unigraphics, which is basically, the next generation system with a new architecture and that has comprehensive CAE capabilities. So in a nutshell, NX, or Simcenter Space System Thermal, as we call it today, is the successor of the ID's TMG. Continuing quickly with history, released a fluid flow solver in 1990 and 1D duct flow network integrated with 3D flow in 1992, and finally thermal flow co-simulation in 1995, always in a tight CAD CAE integration. In 2000, we added thermal electrical joule heating and added two vertical addressing the specific needs of two markets, namely NX SST, or Space System Thermal for space application and the space industry, and NX ESC, or Electronic System Cooling for the electronics industry, but that is also now widely used in the space industry, since there are more and more electronic components in space that need very reliable thermal calculation. In parallel, we developed various modules on the structural side. For example, NX laminate for composite analysis, or NX durability for fatigue calculation, as well as a multi-physics framework which allows us now to exchange information with NX Nastran for well-integrated thermal mechanical simulation. Finally, recently we developed not only a one-way but also a two-way fluid structure interaction capability, or thermal flow Nastran co-simulation, all within one environment. So Space System Thermal extends the capability of the TMG, or the thermal solver, to space application and is used by almost all of the major space agencies worldwide. Key functionalities for space application is enclosure radiation modeling, and Space System Thermal provides advanced capabilities, including non-diffuse, non-gray modeling, or solar planetary heating. Also, the dedicated orbit modeler is a strong offering for simulating thermal response of orbiting vehicles. Open interfaces with other space industry code further strengthen our product. Next slide. So as I already mentioned, Simcenter SST is part of the Simcenter 3D family. So in a nutshell, what it means is that it is based on the best-in-class NX simulation modeling platform. As you can see, this platform allows our customer to tackle many different physics: structures, motion, durability, acoustics, electromagnetics, composites, etc., etc. At its core, you can see that all those functionalities rely on the same pre-post engine, which is called Engineering Desktop, and which is the integrated environment in which you do all your pre- and post-processing. Within this environment, Simcenter 3D offers best-in-class geometry editing tools, comprehensive meshing, and a unique ability to associate the analysis model to design data. This helps you, the thermal engineer, to speed the tedious modeling process and keep analysis models in sync with the latest design. This then translates into faster design analysis iteration. As mentioned previously, Space System Thermal is based on Simcenter 3D thermals with advanced and sophisticated thermal radiation capabilities. Of particular interest to you is the fact that the solver is open and extensible, and because it is so tightly integrated with the other Simcenter 3D products, by nature it has built-in multi-physics design exploration functionalities. Simcenter 3D can link with your broader system engineering processes and tools for 1D simulations and physical testing. Simulation data management lets you track information throughout the development process and can help you correlate your 3D simulation models with your 1D system models and physical tests to deliver confidence that your simulation predicts real-world performance. So this was my very quick overview of both Maya and our product. So I'll hand it over to GF.
Thank you for the introduction. So, my name is Jean-Frédéric Ruel, or JF. I'm an application engineer with Maya. I've been working at Maya for the past 7 years now. And today I want to talk to you about how to really easily include 3D boundary condition data into your thermal models by using inbuilt interpolation methods and user interfaces directly inside Simcenter 3D. So maybe not so long ago, when you wanted to include 3D field data from other CFD codes or different simulation data, you had to write your own Fortran subroutines or your own include files directly into the solver cards. This is a very complicated effort. It's error prone. You need to know how to code in Fortran, which is not always the case. So we take this away when we go to Simcenter 3D Space Systems Thermal. We have an integrated UI that lets you handle 1D, 2D, 3D, and 4D field data. Not only do you not need to code this, you also get the added benefit of graphical checking of these fields. So you can plot these fields in 1D or 2D plots, as well as you can look at 3D distributions of the field as symbols, colored symbols on your geometry, as well as the actual interpolated values directly on your mesh. And so talking about interpolation, you probably, back in the day, if you were doing Fortran codes or your own custom codes, you had to code up your own interpolation methods, or there was maybe one interpolation method coming with your solver that you were using. But with Simcenter 3D, we have all these different interpolation methods hard-coded into Simcenter that are quality tested at every release, so you can be sure there's no errors that are going to be introduced by a faulty interpolation algorithm. And what we see here is just the different interpolation schemes, and depending on how many variables you have in your field, we have different interpolation schemes available. What's also great here is, since you have access to different interpolation schemes, you can play around with different ones and see the impact that it actually has on your on your boundary condition by graphically displaying those interpolated value directly on the mesh. And we'll look at that in my demonstration in just a couple of minutes. So some examples of applications where this can come in handy. For example, if you have high-speed flow adiabatic wall temperatures that you're calculating from a Hyro-Eating code and you want to apply onto your thermal only model, maybe you have some radiative heat fluxes from different sources that aren't included explicitly in your model, but you want to include through fields. You can also map gas temperatures and heat transfer coefficient distributions, and these could be coming from, for example, exhaust plumes of different engines, for example. And these are just a few examples, but there's other applications out there and I'm probably not thinking about. So in those cases, what you really want to get from using Simcenter 3D with the fields application is that, remember, there's no coding required, no user subroutines. You're saving time there because you're not coding up a subroutine. And you're also saving time on checking your interpolation schemes and your data by being able to graphically visualize this. It means you're going to make fewer errors. Also, what's really great with the field capabilities in Simcenter is that once you have units set to your fields, you can convert them to any unit system you want. So you can be flexible, take in SI units and then convert them to British units if you want, or vice versa. Also, this field capabilities is tool agnostic, as long as the tool that you want the data coming from can export the data in a CSV file, so comma separated values, or as a text file, you can import it into Simcenter. You can also use Excel sheets directly to modify the data or simply copy paste the data into Excel. All these things make for a much more reliable process than having to hand code something or to include interpolation cards into an input file for your solver. So I'll try and, so right now I'm going to switch over to Simcenter and show you examples of all these things I've just talked about. So, so here's Simcenter. Since May the 4th is coming up, I had a little bit of fun with the model. So let's assume this spacecraft that has a very funny shape has to fly in atmosphere. And so it has, spatially varying heat transfer coefficient distribution on the surfaces of this model. So my colleague actually ran a CFD analysis on this and sent me some heat transfer coefficient data to a bulk air temperature, let's say. So I would apply a convection coefficient constraint on this model. Convection environment, I simply need to select where this is going to be applied to. And then I want to import the data that my colleague sent me in a comma separated value file. So I'm going to create a new field. And my dependent domain here is convection coefficient. I know that he sent me Cartesian coordinates for the data, but there is a bunch of other independent variables we could be using, and we'll use a few others later on. But for right now, we're going to be using Cartesian coordinates. And now in the definition, here I could type in data, but I'm just going to go in and browse to the comma separated table or CSV file that my colleague sent and directly import the data into Simcenter. Now, I know that this data is actually in watts per meters squared Celsius, so I'm going to go and change the units. But let's say I'm more of a British units guy. I could go ahead and convert these directly to BTUs, for example, hours per inch. But to be realistic, SI units make way more sense. So for this example, I'm going to leave them in watts per meter squared. But you can convert them to any unit system you might want to use. So now that I have this field apply as a constraint, I got the data from my colleague, but it's always good to double check what's actually been imported. So I can actually look at the data of the fields. So this is the raw data. Just all the points with a different color code. But what I'm most interested in is to see how that raw data is going to get interpolated onto my actual mesh. So I can do this and compare both models, both fields essentially side by side. I can do a contour plot of the interpolated values. Let me change the units. So, and let's look at the scale for the plot on the left here. So what we see is that the raw data actually doesn't quite match, at least for the max and min, the actual interpolated data. There is a difference, but just to make a fair comparison, let's switch the max and min values onto here. So 10.98 and 90.26. And so here we go. So we can see this interpolation method's good, but quite not perfect. It is definitely clipping on certain values in the bottom there. So let's try a different interpolation scheme and see the effect it has on these values here. So let's go ahead and I can simply clone this field and go ahead and modify it. So by default, I just use the default interpolation scheme, which is Delaunay fast. But we have access to all of these different interpolation schemes. For today, let's try and compare what we would get with the approximate nearest neighbor interpolation and compare it to the Delaunay. So I have my new field. If I want to do a contour plot, I just need to apply it in a constraint. So I'm going to go ahead and create a new convection to environment constraint. And we're going to just modify it to point to the new field I created with the new interpolation scheme. And we're going to compare the Delaunay contour with the nearest neighbor. Clean up the display a little bit. Change the units. And so on the right here, we have the nearest neighbor, and here Delaunay. So we can see that the nearest neighbor is actually a lot better already, at least with respect to the min and max of the field, if you remember. So for this particular model with this particular mesh versus fields, it appears like I would probably be better off with the nearest neighbor. And this is something I could, this was just 2 of the different simulation schemes. There's still, I think, 5 other ones we could try and check to really pick the one that's best suited for this data and this model. Now, this is a fairly simple example of a simple, you know, a single heat transfer coefficient value with a fixed temperature, bulk temperature. But what you might be getting is a heat transfer coefficient that's dependent on a fluid temperature that's also Cartesian dependent, so spatially varying. And let's do an example of that. So we're going to be applying directly a heat flux to the surface that's based on a heat transfer coefficient times delta in temperature. So first off, we're going to create this temperature versus Cartesian field. So we're going to create a new table. Our dependent domain is, in this case, temperature. And independent, once again, Cartesian. And I have the data this time in actual text format. So I'm just going to go ahead and import that text file. And voila, we have our field. We can take a look at what it looks like. A little bit weird, but that's what I have. And let's just give it a bit more sensible name. So temp field. Now, how do I apply this? Like I said, we want to multiply this convection coefficient with delta in temperature. So the surface temperature minus this fluid temperature, which is the field I just imported. So the way we're going to do this is by creating a heat flux load on the surface of the spacecraft. Heat flux, select where it is applied. And here, what we want is a heat flux. So I'm going to call the fields with the FD function. The FD function is a symbolic expression that gets evaluated by the solver at runtime. So at runtime, the solver will interpolate this field, find the actual heat transfer coefficient. So convection coefficient is the name. You can see it on the left here, convection coefficient. So we're just calling the convection coefficient field we created before that's spatially varying. And we're gonna, now we're able, using the FD function, we're actually able to do operations on this. So for example, I could just multiply it, scale it by 10, but I wanna get a heat flux. So like I said, we're gonna multiply it by a temperature difference. So we're gonna multiply it by the temperature of the surface, which I can get at runtime using this symbolic expression temperature, which is understood by the solver to be the element temperature of the selection, minus the temperature of the field that I created just now, so the temp field, wherever the element that I'm comparing to is, and this will give me a heat flux. So you can see you can do different operations using on the fields using the FD function. Now, if once I've applied this, I might want to be able to know what's going to be applied. And once again, we can do a contour plot of the data. But in this case, since I have that temperature expression, this is actually a temperature dependent plot. So here I can actually look at the heat flux at various temperatures of the wall temperature in this case. So I could change this to 100 C, for example, and see how that changes. We can do static plots, but this might be more meaningful in an animation style plot. So we can also animate through a range of temperatures. And really look at how it changes as the temperature is increasing or, well, in this case, increasing. So what we've done here is created a heat flux, essentially, that is spatially dependent and temperature dependent on, the wall temperature and a fluid temperature. But let's say you have a slightly different relationship for your heat flux and your heat flux. You might have something that is actually temperature and time dependent heat flux. So you could directly create a field that we would call, I guess in this case, a 3D, it's still a 3D field, of where your dependent domain would be heat flux, and your independent domain would be temperature and time. And then you would just have to fill in this data of temperature, time, and then heat flux. Now, depending how you get the data, that might actually be, a lot of work to combine all those things. What you might already have is something like this. So at a specific temperature, so for example, at 100 C, I have a relationship of how the heat flux linearly increases with time for 100 C. And then I have different equations for 50 C and 60 C. Now I could mash these fields together to try and do some Excel copy pasting to try and get a table that's 3 columns wide. But instead, what we can use is the table of fields functionality. So what we have in Simcenter is what we call tables of fields. And this is where you can will be able to reuse these tables and simply say at 100 C, I have this time versus temperature relationship, at 50 time temperature and 60. You'll see as I do it probably better. So dependent domain, once again, is heat flux. Heat flux right there. And my independent domain, just like before, would be temperature and time. And now what I can define is a temperature and then a field. So at 50 C, for example, I have my 50 C field of heat flux versus time. I have at 60, I have this new field. And at 100, we have the last one. So what we're building here is essentially a bivariate table of heat flux that is dependent on time and temperature, but in just a more user-friendly format. You could also do this, for example, if you had different temperature fields, so spatially varying temperature fields at different times or at different temperatures. You could also do something like that. Now that I have this table of fields, this is a heat flux, so I can directly go back to my heat flux load, replace this equation by simply calling this table of fields. And let us say I wanted to know how this is going to get evaluated at 50 Celsius and time 0. I can do by inputting the values here. This will tell Simcenter I'm evaluating this field at 50 Celsius times 0, and the value I am getting is 10 watts per millimeter squared. However, if I increase this, for example, to 100 seconds, this value would turn out to be 110 watts per meter, watts per millimeter squared. So that's another way of graphically checking how this field is evaluated. Now, I could run with this, and the solver will evaluate temperature and time, and based on those, will apply a heat flux. But let's assume that this flux is coming from an engine that's starting, and that engine only starts after a certain amount of time. If I want to add this offset to this load, I can actually add conditional statements directly in Simcenter UI. So without having to code a user sub, I can go and do if-else statements. So for example, if I'm doing a starter, an offset to the start, I can say if my time is smaller than 10 seconds, my motor is off, thus I have a 0 load being applied on my model. However, after 10 seconds, I want to apply that field I defined before. So I'm adding logic to my load without having to code, or we're coding, but essentially directly in Simcenter. We're doing this with time, but we could also do this with temperature. We can do a sort of thermostat check for the temperature of the elements that are selected, or a temperature of a point in the model. And there's a bunch of other map operations and different functions that we have access to directly in Simcenter. And I'm not going to go any deeper into this today, but if that is something that we could probably look at in a next webinar in the future. So keep an eye out for that. So now I'm going to apply this as a load, and I actually ran this, so with just a convection to environment and a heat flux. I ran it before just to save a little bit of time here, but what I want to show you is that so what we're looking at here is the total heat load on the model. So you can see that at time 0, we have 0 load. If I move forward in time, it's 0, 0, 0, until I hit 10 seconds, and then my if-else statement, my conditional argument triggered, and so I have a load now. And if we plot this out across iterations, we can actually see that before 10 seconds, my load is off. After 10 seconds, it's on. And then it follows whatever the time versus temperature field I had specified earlier. So that's what I wanted to show you for today. So we saw how we could directly input 3D data into Simcenter without any coding required. You saw how easy it was. We saved a bunch of time. We could change between unit systems in just a few clicks. We were able to graphically check our data, compare the impact of interpolation schemes on the actual 3D data for our boundary conditions. We imported the data through CSV files and text files, which means we can get this data from pretty much any simulation tool out there. And this proves altogether to be a much more reliable process than what you might have to do if you have to code user subroutines and code your own interpolation schemes in Fortran. So I hope this was informative to everyone. Here's my contact information. If you have any questions, you can contact me. Also, I'd like to mention we're going to be sending out a survey after this webinar to get your feedback on this presentation. And also, there's going to be a question in there about future topics you might want to see in future webinars. So if you can take a couple of minutes just to answer that after, that would be greatly appreciated. Yeah, thank you. Carl, did you want to finish up?
Sure. Thank you, Jean-Frederic and Christiane. We'll now address audience questions, and you can still ask questions using the questions panel of your GoTo dashboard. I have a few already pending, so let's start with those. The first question here is, can you exchange models with Thermal Desktop?
Yeah, maybe I can take that question. So the answer is yes. We've been working on improving. We have various ways kind of to import kind of both some geometrical entities as well as some thermal modeling capabilities. One thing that I may want to add is kind of we are currently looking at ways to improve the import of Thermal Desktop models. So we have something called NX Open, and they have something called TD Open. And so we are working together to try to showcase some examples that could be usable for customers. So we're in the process of starting that project with them.
Great, thanks, Christian. The next question is, you showed how to map 3D data easily. How would you map temperatures to a structural model for thermal distortion analysis?
I'll take that. I guess there's two methods. You could use what I just showed directly in Nastran, but we also have a dedicated mapping solution that's made for mapping temperatures to structural models. The advantage of the mapping solution is that it has extra constraints and controls over the mapping. And so there's essentially two methods that you can do.
Great, thanks, Jean-Frederic. Another question here, it just came in. It says, does Space Systems Thermal support ray tracing for view factor calculations?
Yes, we do. So we have a Monte Carlo ray tracing method, as well as a deterministic ray tracing method.
Okay, very good. We're looking for more questions. If you have any, we'll give you just a brief time here to formulate those. Again, you can use the question panel of your GoTo dashboard to ask those questions. Also, if you'd like to ask them verbally, you can raise your hand, figuratively speaking, and I should be able to unmute your mic. So we'll give you a few seconds here. While we're waiting, Jean-Frederic, could you go to the last slide, please? Very good. All right, so if you'd like to find out if your NASA division has Simcenter 3D installed, or if a trial installation can be arranged for you, please contact Joel Rooks using the contact information on this slide. I'll leave that up there so that you can jot it down. And if there's no more questions, then thank you for joining us today. We'll follow up with an email communication providing a link to today's webinar recording along with a brief survey, as JF mentioned. Please keep an eye open for email announcements detailing future bi-monthly Maya HTT webinars for NASA. Right now, our next planned topic details an automated approach for using ECAD data to thermally represent a populated printed circuit board, including the 3D copper distribution within the board itself, using Space Systems Thermal. So I think that could be of great interest to anybody who has circuit boards in their design and needs to assess junction temperatures and things like that. So this concludes today's webinar. Again, thanks for joining us, and we look forward to working with you again shortly.